This is section 1.4, part A. We're going to do a little bit of review of solving quadratic equations and look at its application to modeling. First of all, when we solve quadratic equations, we have three options, three choices as far as the technique that we're going to use to solve. The first one, usually the quickest one, is factoring. If factoring doesn't work, we normally use the quadratic formula. The third option is the one that we actually looked at just before this. Certain equations are in a good form to use the square root method. And so I want to start, when I look at the four problems in example 1 here, by identifying which ones look like they would work well with the square root method. When I look at the very first problem, 3x squared minus 54 equals 0, I can see that it would be fairly easy to get x squared by itself, and then I could just take the square root on both sides. So I'm going to use a square root method on that one. I'll add the 54 to move it to the right-hand side. Dividing both sides by 3 gives me x squared equals 18. And now I can take the square root on both sides. Once again, being careful to use both the positive and negative square roots on the right. When we were graphing, we often just took answers like this and found the square root of 18 on our calculator to give an approximate answer. But in this section, we're going to look for exact answers. The square root of 18 is an exact answer, but it's not in its simplest form. You can actually break that square root down to simplify it. What you want to do is ask yourself, what's a perfect square that goes evenly into 18? Of course, 9 is a perfect square, and 9 divides evenly into 18. So I'm going to rewrite my answer as the square root of 9 times the square root of 2. Still 18, but just split up a little bit differently. I can now say, well, the square root of 9 is something I can do. It's 3. And then I have the square root of 2. So 3 times the square root of 2 and negative 3 times the square root of 2 are my two answers here. Looking at the next equation, I don't believe that I'm going to be able to solve that one using the square root method, and the reason is I have an x to the first power here. So taking the square root of both sides, I'd have an x under the radical. Not a good choice. So we'll save that one and use a different method. The third example does look like a good option for the square root method. Notice that if I were to divide both sides by negative 2, I would have x plus 3 squared equals negative 24. The left-hand side is a perfect square. I can get rid of that square by taking the square root on both sides, remembering my plus or minus. On the left, the square root is an inverse of the square. They sort of cancel each other out. And I have x plus 3 equals plus or minus. And now we've got something else going on. We have a negative under our radical, meaning we're going to get an imaginary number as an answer. Again, when we were working with graphs, we didn't want that because we couldn't graph imaginary numbers. But now that we're just solving the equation, imaginary solutions are going to be okay. Whenever I have the square root of a negative, I can think of that square root of negative 1 as I, the imaginary unit. And then I'll split up the rest of the problem. The square root of 24, well, let's see, a perfect square that goes into 24 would be 4. So I'm going to write that as 4 times 6. That right-hand side now can be written as I times the square root of 4, which is 2, times the square root of 6, which I can't do. And then to finish, I'll just subtract the 3. So x is going to be negative 3, plus or minus. And usually we write that as 2i square root 6, just kind of standard notation to write the I right before the radical. And there are my two solutions to that quadratic equation. Unlike When I have all real number answers, I can't plug that into my calculator and get a value. The I keeps the first and second terms from being combined. Answers in this form that have a real part and an imaginary part are called complex numbers. And oftentimes we'll have answers that are complex numbers. Unless you're told not to or there's a reason not to, we normally go ahead and give our imaginary answers right along with our real answers, unless I'm doing something like graphing or solving an applications problem. Okay, that leaves us two more equations that we haven't solved yet. So we're going to go ahead and try either factoring or a quadratic formula on those. I'm just going to recopy them down here. The first one was x squared equals 2x minus 6. And the second one was 4 times x squared plus x equals 8. Make a little more space here. When we have a quadratic equation that we're going to solve by either factoring or the quadratic formula, our first step is normally to get that to equal 0. So on this first one, I'm going to go ahead and subtract the 2x and add the 6. And that will make the right-hand side 0. Thinking about factoring that, I would need a sum of -2 and a product of +6. I don't think I'm going to be able to find numbers like that, so I'm going to have to say this one doesn't factor, leaving me with the only option being the quadratic formula. Let's run through that. The opposite of b would be +2, plus or minus the square root of b is -2 squared, minus 4 times a, which is 1, times c, which is 6, divided by 2a. And that's 2 plus or minus the square root. Inside that radical, I have 4 minus 24, which would be -20, divided by 2 again. And once again, I can see I'm going to have a complex number for an answer, because I do have to take the square root of a negative, which always results in an I, an imaginary term. Let's take a look at that. I know I can deal with the negative by just factoring out a square root of -1. And then I have to think of a perfect square that goes into 20 evenly. I'm thinking 4. So we'll rewrite that 20 as 4 times 5. And that's going to give me 2 plus or minus. The square root of -1 is I, and the square root of 4 is 2. So I'll write that as 2i square root 5 over 2. And notice that this time the 2 actually does divide into both terms. It has to divide into both, but if it does, it's okay to divide it out and simplify this one more time, giving me a final answer of 1 plus or minus I square root 5. All right, let's try the next one. I'm looking at that one. I'm going to start by noticing that I could actually make my job a little bit easier by dividing the 4 out of both sides first. I wouldn't do that if it would cause a fraction, but since it's going to divide into everything so nicely, I'm going to go ahead and do that just to make the numbers smaller. Keeps the math a little easier. All right, I now need to get this to equal 0, so I'm going to subtract the 2. And let's see if this one factors. I would need a sum of +1 and a product of -2. And that one looks pretty good. If I use 1 and 2, making the 1 negative and the 2 positive, those will add up to 1. So I think I can factor this as x minus 1, x plus 2. x minus 1 equals 0 or x plus 2 equals 0, giving me solutions x equals 1 and x equals negative 2. It's also worth talking a little bit about how we can use technology, our graphing calculators, to help us solve equations. In general, there are two different ways that you can go about this. One option is when you have an equation, there's two sides, a left side and a right side, and you can just simply solve the equation by setting the two sides equal to one another or by graphing both sides and looking for the intersection point. So if I had the desire to solve the equation f of x equals g of x, f of x in this case is supposed to be the graph of the line, and g of x is the parabola. I can see that those two equations, or those two functions, are going to be equal to one another exactly at the points where the graphs intersect, here and here. In this particular case, it happens to be at x equals negative 1, and again at x equals 3. Notice what I'm trying to solve. I am trying to solve for x, so the y values of the intersection points don't actually get used. They don't tell me anything that I need to know about solving the equation. Another way to use technology or a graphing calculator to solve equations is to get the equation equal to 0 first, and then you only have to graph the non-zero side on your calculator and find the zeros or x-intercepts on the calculator. So that would be, in this case, these 2 points. To solve the equation f of x equals 0, I would say the first point would be at x equal negative 3, and the second of the zeros on the graph was at x equal 5. Again, only the x values are necessary. We're solving for x when we're solving the equation. Let's go ahead and see if we can redo one of our previous examples on our own graphing calculators and solve it and hopefully get the same answers using technology as what we got doing the problem by hand. We're going to look again at the problem 4 times x squared plus x equals 8. We just did that problem a moment ago, and remember that we got answers of negative 2 and positive 1. When we did it by hand. Okay. I'm going to try doing this with a calculator. So let me grab my calculator and bring it over here. The first thing that we'll need to do is to graph, in this case I think we'll go ahead and graph both sides separately since it's not equal to 0. We could get it equal to 0, but we'll look at that process a little bit later. So I'm going to go to y equals, and when I get to the y equals, first in y1 I'm going to type the left-hand side of the equation, which was 4 times x squared plus x. I'll use my arrow key to move down, and in the y2 I'll put the right-hand side of the equation, which was just 8. Let's go ahead and graph these two functions, and for right now I think I'll just use a zoom standard, a window of negative 10 to 10. If you go in your zoom and select option number 6, zoom standard, oops, went too far, there we go. That will automatically set your axes to negative 10 to 10, both the x and the y. So there's the left-hand side, the parabola, and there's the right-hand side, just the line y equals 8. I would like to know where these intersect, where they cross. And the answers that I know to be correct, negative 2 and positive 1, look pretty good, but I want to make sure that that's exactly what I have. So using the second calc menu, I would like to calculate here option number 5, the intersection point. So enter. And it's going to ask me a couple of questions. It's going to say first curve, question mark, I'm just going to say enter. Second curve, again, I'm just going to say enter. And when it says guess, I'm going to use my arrows to move my cursor over so it's close to the first intersection point that I want. And then I'm going to hit enter. And we can see here that we get an intersection at x equals -2, which definitely was one of our solutions. The y value is 8. Yeah, true, but not anything I really needed to know. I was trying to solve for x. To get the other intersection point, let's just do this again. Second, calc, and option number 5, intersect. First curve, enter. Second curve, enter. And then to the guess this time, I'm going to move over and try to get close to the other intersection point before I hit enter. And here's that intersection point at x equals 1, y equals 8. Again, the 1 is the part that I really was concerned about, and that does match my answer that I got by hand. So our x equals -2 and our x equals 1 we once again got for solutions. In addition to solving equations, we would also like to be able to solve inequalities, problems that have less thans and greater thans in them. And we're going to use a consistent method to solve inequalities throughout this course. I like to use a number line testing method, so I'm going to show you that for the first time today. But again, you're going to see this with other types of problems throughout the course, so it's a good one to really concentrate on and learn right now. The first thing I like to do is get 0 on one side, so I'll go ahead and do that. And in fact, let's do that right now. In this first problem, if I were to subtract the 7x and subtract the 10, my problem would just be greater than 0. Next, I'm going to solve what I call the related equation. Simply replace the inequality symbol with an equal sign and solve it. So if we just pretend for a moment, oops, I'm sorry, that was equal to 0, not 10 there. I have my choice of how to solve this. I can try to factor it, or I can use the quadratic formula. This one may actually factor. Let's try it. If I were going to do a sum of -7, and the product this time has to be 6 times -10, or -60, I think that's going to work out. I could use 5 and 12. I put the negative on the 12, those will add up to -7. So I'm going to take my equation, 6x squared, and then I'm going to rewrite that -7x as plus 5x minus 12x minus 10 equals 0. And now that I have 4 terms, I can use factoring by grouping here. Factoring out an x gives me 6x plus 5. I've got a minus between the groups, so I'm going to factor out a -2, which also gives us 6x plus 5 equals 0. And I now have the common binomial, 6x plus 5, which I can factor out, leaving me x minus 2 equals 0. So either 6x plus 5 equals 0, or x minus 2 equals 0. In the first one, I would have 6x equals -5, so x would be -5 divided by 6. And over here, I would have x equals 2. Now, if I had an equation instead of an inequality, I would be done. But I did have an inequality, so I'm going to go back now and say, all right, the -5/6 and the 2 are really just points that tell me where to divide up the possible answers. What I like to do at this point is draw myself a number line and take all the solutions to the related equation and just place them on the number line, like that. There's a section to the left of the first answer. There's a section between the answers, and then there's a section to the right of the second answer. And any of those sections could be the answer to my inequality. I could have one section, I could have two sections, I could even have all three sections. In order to decide, I'm going to use some test values. I'm going to first of all pick a number over to the left of -5/6, perhaps -1, which is certainly smaller than -5/6. And I'm going to test that value. Oops, not in there, sorry. I'm going to test that value in the original inequality. If you were to plug -1 in for x, you would get 6 times -1 squared minus 7 times -1 minus 10 is greater than 0. And let's see, that would be 6 plus 7 is 13. 13 minus 10 is 3. And 3 is greater than 0. So my inequality is true in that section of the graph. If it's true for one test value, it will be true for all values in that section or that area of the graph. Let's pick 0 as a test value in the next section. A nice number because 0 is so easy to work with. If I plug 0 into my original inequality, I'm going to get -10 is greater than 0, which of course is false. So that whole section is going to be false. Finally, I'll pick a number bigger than 2, perhaps 3. And if I plug that 3 in, I'm going to get, let's see, 6 times 9 is 54, minus 21, minus 10. It's going to be 23, which certainly is greater than 0. And so my inequality is true there. Okay. The final solution to the inequality, I'm going to write in interval notation. And I'm just going to pick any of the intervals that are true. So in this case, the first true interval went from -infinity to -5/6. And then I had a section that was false, so I'm not going to include that. But I am going to include the second true section, which went from 2 to infinity. And that's the answer to my problem. Notice, by the way, that I've used parentheses rather than brackets. And the reason for that is, again, looking at the original inequality, it was strictly a greater than sign, not a greater than or equal to. Had it been greater than or equal to, I would have included the endpoints, and I would have used brackets on the -5/6 and the 2. Okay, let's try another one of those. This next one, 4x squared minus 3x plus 5 is greater than 0. I've already got the 0 on one side, so the first thing I'm going to do is just change it to the related equation. 4x squared minus 3x plus 5 equals 0. If I wanted to try to factor this, I would need a sum of -3 and product of 4 times 5, or 20. Looking at that one, I don't believe that's going to work, so I don't think I'm going to be able to factor this one. Instead, let's use a quadratic formula. The opposite of b would be 3, plus or minus the square root of -3 squared minus 4 times 4 times 5 over 2 times 4. That's 3 plus or minus the square root. Under that radical, I've got 9 minus 80, or -71. Okay. Notice we got imaginary zeros here. And remember, the next thing that I'm supposed to do is take the solutions to the related equation and put them on a number line. Now I can't put in imaginary numbers on a number line. So I'm actually going to stop right there and say, okay, if I make my number line, there are no points to put on it. So I can pick any test value I want. Let's pick a test value of 0. Once again, I'm going to plug that back into the original inequality. And if I were to plug 0 in, I would just get 5 is greater than 0, which is certainly true. Because there are no points dividing up the number line, if it's true at 0, it's true everywhere. And I'm going to say the solution to this inequality is all real numbers from negative infinity to infinity. Had I gotten a false there, I would have had to have said there are no solutions to this problem. That inequality is never true. But this one is. It's true not only at 0, but it will be true everywhere. And so my solution is all real numbers. Just like before, it's possible to solve inequalities graphically, just like we did when we were solving the equations. My first option here is when I have a function on each side of the inequality. It's not yet got 0 on one side. And in a case like that, when I want to solve f of x is less than g of x in this particular case, I'm looking for the portions of the graph where f, the line, is below or smaller than g, the parabola. So this portion of the line is below the parabola, and again this portion of the line is below the parabola. Now my answers, remember, are actually x values. So the x values that correspond to the portions of the line that I just highlighted would go from -1 down towards minus infinity. And again here, from 3 to positive infinity. And that would be the solution to that particular inequality. Another option, if your inequality has got 0 on one side, is just to go ahead and graph the one side and then use the zeros to help you determine where it's greater than or less than 0. So if I wanted to solve in the second graph, f of x is greater than or equal to 0, I'd just be looking for the portion of the graph, that's above the y-axis. Get rid of that little extra part there. This part here. I can see that that happens for x values that are between -3 and 5. Notice this time my inequality had not just a greater than sign, but a greater than or equal to sign. So this time I want to include the endpoints, and I'm going to use brackets on that answer. All right, let's redo our two problems using the graphing calculator and see if we can come up with the same answers that we came up with by hand. First, if I want to redo the problem, 6x squared is greater than 7x plus 10. In this case, there's not 0 on one side, so let's go ahead and graph the two sides separately. Back to y equals, I'm going to clear the previous equations out. And let's see, the first one was 6x squared. And then the other side was 7x plus 10. I believe I still have my zoom standard, my standard window from -10 to 10 in here. But just to be sure, we can go ahead and select it again. Option number 6, zoom standard. There's the parabola, and there's the line. Now this time, that window didn't work out too well, because notice I can see this intersection point, but the other one's up here somewhere off the top of the screen. So let's adjust the window to account for that. I need to see a larger y value. So I'm going to change my y max to 20 this time. I actually didn't need to see quite so much on the x-axis. So maybe I'm just going to go -5 to 5 there. And graph again. Yeah, I'm closer, but I still can't see the intersection point. So I guess I need to go a little bit bigger yet. On my window, let's take it all the way up to y equals 30 this time. That should cover it. And there we go. Now I can actually see the two intersection points. All right, I would like to know where 6x squared is greater than 7x plus 10. So I'm looking for the parts where the parabola is bigger than the line. This part and this part. And I will need the two intersection points. So we can find those by going into second calc. Option number 5 is intersect. First curve, enter. Second curve, enter. And if I get over close and enter, that first one is negative 0.83 repeating, which is actually the negative 5/6, just the decimal form of it. And if I do this again, enter, enter, and this time I want to move over so that I'm close to the other intersection point before I hit enter. And there's that x equals 2 that we found before. So again, the x squared, the 6x squared, the parabola, is larger than the line from negative infinity until I get to the 5/6, and again from the 2 to the positive infinity. All right, let's take a look at the other one. In our second example, we had 4x squared minus 3x plus 5 is greater than 0. And since we do have 0 on one side this time, let's use the second option. Let's go to our y equals. And I'm going to clear the equations that I had in there from before. And we'll just put in the 4x squared minus 3x plus 5. And let's see, I'm going to go back to a zoom standard on this one. Negative 10 to 10 on both axes. See what happens? What we see is a parabola that always stays above the x-axis. It never dips below. Its vertex is higher than the x-axis. So since I wanted to know when is this function larger than 0, it's always larger than 0. All those y values are positive. And I'm simply going to say x can be anything from negative infinity to infinity. If you'd like to continue and try some practice problems for yourself, there are several practice problems that follow this in your notes. You can try those and check your answers, and then come on back for part B.